And with no further delay, we'll move into another talk about DSP. So this is a great meetup for DSP aficionados, and this talk is another edition of DSP Corner. So as you may or may not know, Rachel Locke, my co-host, has been giving monthly discussions on fundamental digital signal processing concepts. So if you want to make limiters, make compressors, delays, these are some of the fundamental techniques that you may want to learn about and know about. And Rachel is a recent graduate of the University of West London with a master's degree. I'm not going to say it's in digital signal processing. It's in something slightly related to that. It's like music. It's in something, the technical name is something very misleading.
It's
but
digital audio engineering.
Digital audio engineering.
Which is quite misleading, yes.
Yes, but she studied digital signal processing, and she's been nice enough to give us these monthly presentations to help other people like myself learn the fundamentals. And today she's going to talk about another fundamental, which is complex numbers. And I will let you take it away from here, Rachel. Take it away.
Perfect. Let me just see if I can share this. One moment. Are we seeing the slides?
Yep, you're all good.
Perfect. Let me just slideshow it up. I feel like I say this at every DSP corner, but I'm getting a bit of a scratchy throat, so I promise I'm not always ill. So please bear with me if I need to take a drink of water or if it gets a bit husky. Thanks for the introduction, Josh. Yep, this is the third episode of DSP Corner. And I would say that Josh mentioned DSP aficionados, but perhaps this segment is a bit more for your DSP beginners or intermediates. Maybe there'll be something if you're already quite deep into DSP, but I'm not quite sure. But you might still enjoy it, and nice to have a primer and a recap. Today we're going to talk about complex numbers, because complex numbers, they're not always like an immediately obvious area that you look into when you look into signals, but just because signals don't naturally have, they're not naturally complex, but we will see why it is useful to be able to represent signals in a complex way for things like the Fourier transform. Yeah, let's get into it. I'm just gonna move, sorry, the like chat bar was in the way. Okay, ready to go. So, at some point in the history of mathematics, dating as far back as like the 14 to 1500s, mathematicians realized a need for a number that gives a negative result when squared, i.e., some number to the power of 2 is equal to a negative result, or -1, let's say. Now, we're probably all quite familiar with real numbers. These are the numbers I've got on the side, got some examples here. They're the numbers you learn when you're learning to count. And basically any number you can think of at this point until we get into imaginary numbers. And if you think about squaring any of these numbers, positive or negative, the result when squared is always going to be a positive real number. So at this point, we can appreciate that any real number squared gives a positive result. You can try squaring 5 squared will equal 25. That gives you a positive result, not what we're looking for. You can try squaring -2, and it will also give you a positive result of 4 because the minuses will cancel out from the squaring. There existed no such number x where x squared equals to -1. So mathematicians decided to invent one, which they called the imaginary unit, I, defined such that I squared is equal to -1, and that I is equal to the square root of -1. In this introduction to complex numbers, I'll use both I and j to refer to the same quantity, the imaginary unit. J is often used instead of I to represent the imaginary unit, as in electronic engineering, I is reserved for current. The invention of imaginary numbers gave way to the possibility of complex numbers. Complex numbers are the numbers that have a real part and an imaginary part. The form in which I've introduced complex numbers is called Cartesian or rectangular form. It has a real part A and an imaginary part BI. We will now attempt to visualize some complex numbers. To appreciate the use of imaginary and therefore complex numbers, it is useful for us to visualize them on a plane. First, consider the real number line. This is the familiar number line that we've been taught to count on from a young age. The real number line will form our x-axis, which we'll refer to as our real axis. Now we'll place an imaginary number line perpendicular to our real axis. This will be our y-axis, and we'll refer to it as our imaginary axis. This type of diagram is called the complex plane, or sometimes referred to as an Argand diagram. As we previously introduced, a complex number is a combination of a real and an imaginary number, and can be visualized on the complex plane as a point. This has coordinates real, imaginary, relative to the origin. The visualization of complex numbers on a complex plane is an important step to understanding complex numbers. We can see here that this complex number Z1 has a real part on the real axis of 4, denoted by the dashed line, and an imaginary part of 3i. Let's plot another complex number, Z of 2. This point has a real part of -2 and an imaginary part of +1i. Finally, let's plot a third. This complex number has a real part of 2 along the real number line and an imaginary part of -4 along the imaginary number line. It's useful to note at this stage that complex numbers can have either a real or imaginary part that is 0. If the real part is 0, then the number will lie on the imaginary axis. Conversely, if the imaginary part is 0, the number will lie on the real axis. As you may know, the values of measured audio signals are not inherently complex. However, representing signals, real signals with complex numbers can be extremely useful at times. We often wish or find it advantageous to break down a signal into a variety of component sinusoids at different frequencies. Hence, complex numbers are significant in signal processing. More on how this works in a later episode when we look at the Fourier transform. For now, just know that when we perform a Fourier transform on a signal, each frequency component in the output has a magnitude and a phase. This is actually a complex number whereby the real part is the magnitude and the imaginary part is the phase. Complex numbers also have a magnitude and a phase, which we'll see in a moment when we begin to visualize them in polar form. Therefore, it comes naturally to use complex numbers to represent the magnitude and phase of sinusoidal components. Again, measured audio signals are not inherently complex valued. However, sometimes it can be really useful to represent these signals with complex numbers. It is often useful to be able to measure the phase of a signal, which may be done easily using trigonometry if the data is represented as complex numbers. Following this, an alternative way to represent complex numbers is from the origin is by the distance from the origin, which we will call the magnitude, and denote as r, and the angle from the real positive axis, which we will denote as the Greek letter theta. We can now see that we have a right-angled triangle and that our magnitude r is the hypotenuse. We can now calculate the magnitude with Pythagoras theorem. Polar form is often represented, as we see on the left here. Z, the complex number Z, is equal to the magnitude r, and this symbol next to r is, in mathematics, an angle symbol. So a magnitude of r and an angle of theta. We can see that on the right angle triangle, we have an adjacent and an opposite, and this will help us calculate the angle theta in a moment. First, we can calculate r with the Pythagorean r equals to the square root of a squared plus b squared. And we can see from our complex number that our a is 4 in this sense, and our b is 3. So let's plug those numbers in and see what we get. We simplify it to the square root of 25, and then we get the answer 5. So our magnitude r is equal to 5. Next, we want to get the angle from the real positive axis of our complex number. We know from trigonometry that tan of theta is opposite over adjacent. But we don't exactly want tan of theta. We want to have theta on its own. So we can do this by taking the inverse tangent or the arctangent of opposite over adjacent. Let's plug those numbers in and see what we get. Our opposite is 3 and our adjacent is 4. Our angle is in degrees and it's 36.87. We can now represent this in polar form. Oh, I think I meant to have, I was meant to have the answer in polar form there, but in polar form it would be now 5 angle and theta would be 36.87. Okay, so we can actually use the same rules that we do for arithmetic with real numbers with complex numbers. And we can see that there's a few different forms of complex numbers shown on this page. And we're going to look at which forms are best for which kind of calculations. So for simple addition and subtraction, the best form of a complex number is what we call Cartesian or rectangular form, which is the first form of complex numbers that we saw. And you've got this up the top as z equals a plus bi. And I've got a couple of complex numbers here, 5 plus 9i and 4 plus 7i. And if you want to add two complex numbers, all you have to do is separate the real and imaginary parts. And what you're going to do is you're going to add the real parts and add the imaginary parts. And if we plug in the values from these numbers, we can see that if we add these two complex numbers together, we get 9 plus 16i. Similarly with subtraction, we subtract the real parts of the complex number from each other and subtract the imaginary parts of the complex number from each other. If we plug in the values from our two complex numbers in Cartesian form, we're left with 1 plus 2i. Now, in order to multiply and divide complex numbers, we can also do this in Cartesian form, but it's a bit more lengthy and involves the FOIL style of multiplication or division, whereby you're taking the first and then the outers and the inners and the last. And what we could do instead is translate this complex number to polar form, which we just saw. Or alternatively, another form called exponential form, which is made possible by Euler's formula given in the top right-hand corner of the page here. More on that formula in the next slide. And by using polar form or exponential form, multiplication and division of complex numbers is made easy because we can just multiply the magnitudes of the complex number together and add the angle or the phases. And we can see that so these complex numbers up here, they are actually the conversion of the ones I just showed you. I converted them earlier. We can see that if we want to multiply two complex numbers together, we can add the two magnitudes r. So in this case, we've got 10.30 and 8.06. And we multiply them together. And then in the exponent, we add the angles. And we're left with this rather confusing looking number, which in the first half before the e is the resulting magnitude of the multiplication. And in the exponent of the e, we have the complex variable j, and then we have our resulting angle, which is 121.21. Then in terms of division, we can divide the radiuses and subtract the angles. So it's just kind of the other way around. Instead of doing addition on the angles this time, we do subtraction, and then we divide the radiuses. So if we plug those numbers in again, same numbers, we can see that we're left with this resulting complex number in exponential form. 1.28 is the radius, and the angle is 0.69 degrees. Okay, now we're going to look at Euler's theorem, or Euler's formula. And this is another representation of a complex number. And we can start to see cosine and sine, which are familiar functions to us as audio programmers. And what we're going to do is we're going to plug in some numbers, just some arbitrary numbers for x here in Euler's formula, and plot them on the complex plane. So let's start off with 1.5. If we plug in the numbers for cosine and sine of 1.5, we're left with this complex number. Let's plot that on the complex plane. Let's choose another arbitrary number 4. And let's plot that one on the complex plane. Let's choose another number and plug in the values for cosine and sine and plot that complex number on the plane. And let's choose one more. 2.5. And let's plot that on the plane. Now you might see at this point that a pattern is emerging at the points where we've plotted these complex numbers based on Euler's formula. And that is that they are all plotted on a unit circle that has a radius of 1. And this is one of the main points of Euler's formula, that everything you plug in for x here will be a value on this unit radius circle, and the distance around the circle will be denoted by the angle theta. And on the other side of the screen here, I've done a bit of a zoomed in plot to show what I mean. So we can see from Euler's formula that the real part of the complex number is cosine theta, and the imaginary part of the complex number is j sine theta, and that this whole complex number is denoted by the term e to the j theta. And theta is just the independent variable in this case. So it means that whatever the angle of theta is will determine how far around this unit circle this complex point is. Now, if we want to visualize this in terms of rotation, which is important for plotting sine and cosine, I've got some animations in the next slide which should help with that. Here we go. So I want you to imagine that you are in the plane of the slide and you're looking where this eye is looking down this axis, which is labeled X, but that would be our real axis from what we've just seen. And what's labeled I would be our imaginary axis. So if you're looking down this axis X, and you're within the slide, you wouldn't have depth of field, so you would only see this red dot going up and down. You wouldn't be able to see the black dot rotating, you would only see the red dot going up and down. And that red dot, in terms of an imaginary number line, is oscillating between plus I and minus I. Or in this case, we've got +1 and -1. And you can see it tracing the sine wave, which backs up our theory that we just saw the sine as the imaginary part of the complex number. And you can see that in this animation here. I then made a rotation of this animation so that we can look down the imaginary line. And this time, if we were in the plane of the slide, we could see this blue dot going up and down, oscillating between 1 and -1. And this is tracing a cosine. And that is the real part of our imaginary number when expressed with Euler's formula. So I hope that helps to visualize a bit how the rotation would work as theta increases. You can see the theta increasing as the black dot moves around the circle. Finally, let's introduce complex phasors and real signals. Consider a complex number whose magnitude is 1, as we just saw with Euler's formula, and whose phase angle increases with time. As this complex number has a magnitude of 1, it will characteristically lie on the unit circle, as we previously saw by plotting complex points using Euler's formula. As time t increases, so does the complex phase angle theta. Our complex point traverses around the unit circle in an anti-clockwise direction. This is identical to the rotation we just observed in the animations in the previous slide, but this time we consider a complex number that is a function of time, and therefore the rate at which it rotates on the unit circle is determined by the frequency f. For example, if the frequency f equaled 10 Hertz, the point would rotate around the circle 10 times per second. Now, this is a bit closer to what we introduced in DSP Corner 1 when we spoke about the mathematical representation of cosines and sines. And I've put it here in terms of Euler's formula to see how similar this is to how we represented our cosines and sines when we first looked at them. I've also put at the bottom of the page that you could swap out the 2 pi f, which is our frequency, with this omega, which is our angular frequency, which we also saw in the first DSP corner. So that's just to show that you've got this relationship between 2 pi f and omega, and you could swap them out and they would mean the same thing. The complex exponential in the lower right quadrant of the unit circle is what we call the complex conjugate. This complex exponential has a negative frequency and will rotate clockwise around the unit circle as time increases. We'll discuss how negative frequency relates to the Fourier transform in next month's DSP Corner. So I hope you'll join me again next month to discuss that further. Thanks for coming to my talk, and I know that complex numbers and imaginary numbers is a really abstract concept, so if this is your first time seeing these kind of things, then please like watch some more videos on it. I'll put some more educational videos in the drop down of the talk when it goes up on YouTube. And please like feel free to go through slowly and pause the video and look things up. And yeah, as usual, if you have any questions or concerns, please reach out to me.
Fantastic. Thank you so much, Rachel.
Thank you. Let me stop sharing.
And how can people reach out to you if they have any questions?
So I'm on the Discord.
Awesome.
Yeah.
Rachel
audio
Locke.
programmer audio programmer Discord as Rachel Locke.
Yeah.
I am on LinkedIn as Rachel Locke. I am on Twitter as Madame Modular. I think that's it.
Yeah. Great. So Twitter, Madame Modular, LinkedIn, Rachel Locke, a Locke with an E at the end, and on the audio programmer Discord as Rachel Locke as well.
Thank you. I hope that was helpful for some people.
Yeah, people found it helpful for sure. And one question that I have, and I know that that you aren't really taking questions, so maybe Jarrett can chime in if he has any thoughts. I just want to make sure I understand this properly in my head. So normally I think of an audio signal as, you know, when you draw it on paper, you're drawing it with an X and Y axis, and you're thinking of it in terms of phase and you know, how and values between plus and minus one. So would it be fair to say that the complex plane is the third dimension of that, and that the waves are actually three-dimensional, and the Z plane is just referring to, like, if we could pop a value off of the paper in the third dimension? Is that fair to say, or is it more complicated than that?
So there's actually really good like diagrams or animations that show a third dimensional axis of time coming out, and then you'll get this like kind of spiral or helix shape as that rotation happens and as the real and imaginary part are traced out.
Got it.
So maybe I'll put some links to that kind of animation.
Yeah.
And, do you think that answers it, Garrett?
Yeah, you get the sort of the complex exponentials that you've got like the real value and then the imaginary one, and like time, and it kind of, you see it spiral, and then yeah, that's nice and intuitive.
Got it. Awesome. Thank you very much, Rachel. Yes. So as we mentioned before, if you haven't joined the community, what are you waiting for? Join us. You can join us on our Discord. We have over 7,500 members from all around the world, all different levels of experience. And you can join us on theaudioprogrammer.com/community. And with that, we'll move on to our next talk.